You'll remember from Bayes' theorem that the probability of H1, let's say, given your data, sorry, there's Bayes' theorem that we've covered many, many, many times. The purpose of this is to make all the probabilities add up to 1. We've seen it's A over A plus B plus C, or however many you've got. If you're not interested in the fact that the probabilities add up to 1, then just get rid of it. Which I can do on the board, but you can't do writing. If I'm not interested in the prior, I can get rid of that term as well, and we're just left. It's not equal anymore, but it's a. That's the mean. This is the bit that does the work. In Bayes' theorem. This is the bit that does the work. And you can see when I've just casually got rid of all those other bits and pieces, that is why I can multiply this by an arbitrary constant to get the likelihood. So the likelihood equals constant times probability prob of D given H, I guess. And that constant is standing in for all the stuff that I got rid of with my fingers when I was rubbing it all out. Observe carefully. Oops. The data is fixed. It's the hypothesis that changes. Because I can put different hypotheses into this slot here, but the data stays fixed because I write it down. So it's on the board, I can't change it. But the hypothesis I'm considering can. I can consider different hypotheses. I can consider, 50-50 coin or 60-40 or 90-10. I can move that around. And of course, what we got at the end of the day was a beta distribution. So let's consider, just as an example, I'm just reminding you what's happening because I'm going to work up to log likelihood. Consider, let's say, 9 trials. We have 2 successes and 7 failures. That's D, which is now fixed. So the probability of data given P for the probability of success, which is my likelihood here. I haven't put the constant in. I'll put that in a minute. The reason I'm going through this is that lots of people separately yesterday asked me about this. Okay. And when we plot this, that's the probability. So you write down the likelihood of P equals a constant times 10 choose, oh no, it's 9, I'm sorry. 9 choose 2 P squared 1 minus P to the 7. Where C is an undetermined constant that can be anything. And I went through this a load of times. And so I can't be bothered to calculate that. That's just a number. That's just a number. Who cares? Forget it. Forget it. It's just a constant times P squared 1 minus P to the power 7. Because that constant there, I've got rid of it now, but that's all the bit that I chucked out from Bayes' theorem. So I may as well say C equals 1. Why not C equals 1? Because that's a nice easy. I can't say 0. That would be my first choice. But then again, it would collapse down to nothing. So I've got P squared 1 minus P to the power 7. So I'm going to plot that again. P becomes a sequence from 0 to equals 1, length equals 100, plot P squared, 1 minus P, 7. So there it is. There's our likelihood function here, or a likelihood function. English is a poor language for talking about this because you quite often say we'll calculate the likelihood function. But you can have any C you like. I put 1 in there because I felt like it, but I could have put 10 or 100 or 0.0001, any number in there. You'll remember this from last time. So really, you're talking about, the technical term is an equivalence class of functions, all of which are proportional to one another by plugging in different values of C here. So you don't talk about the likelihood function, because I could just as easily multiply this by any value and it still looks the same. Still the same, all that's changed is the numbers on the axis. It's still the same shape. I want to say again, because it confused the living daylights out of me when I was learning this stuff. The data is in here and here. The data, the 2 and the 7 are the data. Fixed. We've written it down on the board and it's not going to change. It's there. I'm not moving it. P is now variable. The likelihood is a function of P because I can slide, well, you can see, oh, I've covered it up now, but you can see that P is moving around. So the way to think about it is this. I'm wondering what P is. I don't know. It's between 0 and 1 because it's a probability. How likely is it that it's 0.4? How likely is it it's 0.2? I'm asking a question, but the data's fixed. It's on the wall and I can't change it. It makes sense to consider the log likelihood equals the log of C times the probability of D given your hypothesis. It's plus because the log of the product is the sum of the logs. And again, this C here is an arbitrary constant, and we do not know C. We don't know or care what C is. Because it doesn't make any difference. I don't care what it is. It's like saying I'm going to consider potential energy, where I'm lifting up a weight and letting it drop down, and I've got to push energy up and pull it down. And you say, well, I'll move it up 3 centimetres and down 3 centimetres and move it up a metre, and that takes a lot of energy. And then somebody says, yeah, but moving it up and down relative to what? Sea level, ground level, floor level, top of the atmosphere? I'll say it doesn't matter. I'm only interested in changes, up and down changes for potential energy. You can put your 0 where you like. Sea level, doesn't matter where you put. The changes are the same wherever my datum is. And it's the same with this. This is like changing your potential energy calculations from sea level to ground level to the top of the building to the bottom of the building. Okay? It doesn't make any difference. I've still got to do work pushing my weight up wherever my ground level is. That's just here. So let's have a look at the log likelihood. Another word for log likelihood equals support. So sometimes you'll see, the word comes and goes in the literature. It's also got another meaning as well, which is a bit confusing, but it basically equals the log of the likelihood. So you talk about the method of support or the method of maximum support. So let's have a look at the likelihood for this case. Remember, the data's fixed, it's stuck there, I'm not going to change it. So in this case, the likelihood for P equals some constant times P squared 1 minus p to the power 7. And therefore the support of p, which is the log of the likelihood, is log c plus log p squared 1 minus p to the power 7. Equals log c plus 2 log p plus 7 log 1 minus p. You see, because the powers multiply, and I'm multiplying by 7 here. So it's a very simple, and this is an arbitrary additive constant. Let me show you how that works. Get rid of this. And there's my log likelihood. You see, it falls down to very, very small levels of minus 30, so that's 0.000001. So it's because let's just, instead of going down to, let's just go down to minus 10. When I put y lim in, it sets the vertical limits of the plot. So we can see a bit more detail here. There you go. So there's my log likelihood, and I'll put a grid on it. So here's my log likelihood curve, which has come up for the maximum one there of about here, 0.22. But we can see that it falls off. So that's the maximum likelihood estimate, or the maximum support, because I'm plotting it on a log scale. But I'll just show you what happens if I go point. Oh dear. Oh, that's not good, is it?
Usually down by 8. I think there's a.
I've raised this one here. I've phoned 9888. Oh, thank you.
It's just this box. It's like a switcher box, and if you knock one of those inputs,
Oh, right.
you can't really push it back too much further.
Oh well, I'll just put my chair there and see if I can. Where was I? So I've got the plot. If I say points, it'll just put points on an existing plot and not overlap them. Yeah. So if I'll put 5 times that. The support curve is here, and instead of an arbitrary multiplicative constant, I've got an arbitrary additive constant, which is now the log of c, which takes this curve and moves it up. But you can see it's the same shape. It's the same information in it. So I'm just going to go back to that one with a constant of 1, because it's easy. I can't be bothered to put, I could do if I wanted, put any number in there, but I'll just go there. We can see, you need calculus to see it permanently, but p hat equals the maximum likelihood estimate of p equals 2/9, equals 22.22%. Okay? Because we've got 2 successes out of 9 trials, yeah? We've talked about this. This is the maximum one. So I can work out the maximum amount of support, which is this. Log of 2/9 to the power 2 times 7/9 to the power 7. All I'm doing is taking my I can write it out more easily, just a minute. That's my maximum likelihood estimate, 2/9, because I've got 2 successes out of 9 trials. So what I'm doing is working out the support at p equals 2/9, which is this value here. So I'm just taking my log likelihood function, which is this thing here, and I'm just substituting p equals 2/9. There it is. And 1 minus, I put 7/9 in, but 1 minus 2/9 is easier, yeah? To the power 7, because that's what my likelihood function is. And it comes out to be that. Which is negative, and you think, oh my God, it's negative, what have I done wrong? Nothing. If you don't like that negative, just add a constant to it. straight through the middle. Do you see what I've done? I've found my maximum likelihood estimate for P. I've taken the logarithm of it because I'm working in a logarithmic coordinates. And do you see how it exactly finds that value there? I'll draw the vertical line through it as well. Oh, no, it won't. You see, quite directly, I've found the maximum likelihood value of P, which is 2 nines, 2 successive 9 trials. And it is the estimate because that maximizes the likelihood, which is that point there in the crosshairs there. Nice, eh? It's nice, yeah? So what I'm going to do, I'm going to go back to my plot. Is this one here? Should be a plus because I'm subtracting a minus, which is adding. I'm just going to add that on because I can add what I like. Remember, mostly I'm just adding 0 because it's easy. Now I'm going to add that, and you'll see why now. Now it makes the maximum likelihood, the support here, 0. So that's as good as you can do. If I say to you, you can choose P to be whatever you like. You choose it here if you want, but you've fallen down in support. The likelihood's got smaller. So the log likelihood has got negative. Sorry? Sorry? No? Oh. But of course, that's the best you can do. So now, I can put a grid on it. And we can see there's the likelihood value here. Oh, it's not very clear, is it? Let me do that again. So I've adjusted the vertical direction, vertical placing of my curve. Why? To make this point have a support of 0, log of 0. So we can fall off and off and off and off here. Now, in the same way, and so what you really need is some cutoff criterion for saying whether a hypothesis is OK or not. In just the same way that we need a p-value of 5%. Where does that 5% come from? Well, Fisher pulled it out of thin air, basically. And if he can do that, I can do that. So what I'm going to do is just arbitrary. I'll plot it again. There it is, at 0. Horizontal line at 0. And for no reason with any justification more than because it seems to work, I'm just going to say that my support limit of -2 is OK. All right? So outside here, that's no good because it contradicts the data. If the probability really was 0.9, you never, ever, ever see the data that we got, which is 2 successes out of 9 failures. Or to think about it another way, if I hypothesize that P equals 0.6, I've got so much support, but I can get so much more by climbing up here. Yeah? Or, let's just put some vertical lines on this. Vertical at 0.5. Let's just say I hypothesize it's 0.5. I don't reject that hypothesis because it's above the -2 line. So this is 50-50, right? So what I'm saying is if you observe 2 successes out of 9 trials, remember, this is fixed. This doesn't change. What this is doing is giving me the form of the curve. So if I see 2 successes out of 7 trials, and then I ask, is that consistent with P equals 0.5? The answer is yes, because I can't gain very much likelihood by climbing up to this point here. But instead, if I ask, is P equal 0.8, then yes, because I can gain a pile of likelihood by moving from this point up to the maximum likelihood estimate. That's why I scale it to 0, because I can just read off how much extra likelihood I can get or how much extra support I can get from a given hypothesis. So we can even work out a range, and I could solve these equations if I wanted to, but we've got a nice little range in here that gives me a nice, it's not a confidence interval, I haven't covered confidence intervals properly, but it's kind of a credible set of P. I can reject the hypothesis that P is outside these values here, which is nice. So it gives you an uncertainty estimate for how big P is. Quite large, don't you think? From about, what's that, 0.1? Up to about, what's that, 0.6? Quite a wide range. It's wide because we ain't got very much data. Let me give you some more data and see what happens. First step, get rid of my arbitrary constant. Second step, I'm just going to arbitrarily give you 10 times as much data. Now we've got 90 trials. Boink. It's not appeared because I've got my old limits for my y-axis on. See, most of it's in crazy bonkers land. Most of it's crazy because, look, it's going down to minus 300. Remember, that's e to the power minus 300, which is astronomically small. So most of it's in the kind of crazy. We're only really interested in this top region here. And I can control the y-axis quite easily, but what I'm going to do instead is control my p's. If I put a grid on this, oops. Really, I'm interested. Oh, the grid's not come out very well on that. Really, I'm interested, well, let's just say about 0.1 to 0.3. That's where all the action's happening. Most of it's just like crazy. So I'll just redefine P. And now I'm focusing into that interesting region here. And then I'll just plot it again. That's better. So you see it starts at about minus 4. It doesn't matter what that value is. It's just how it could be minus 100, minus 101, 102, 103. So I'll go through the same process again. $20. Of course, it's 10 times the other one. Losing my touch. Is that right? There you go. Same curve. All that's happened. What have I done wrong there? It should be. I was going to say, look, it's 0, but it's not. I've screwed up somehow.
Shouldn't it be log 2 over 9 to the 20?
Oh, well spotted. There you go, and there's your 0. Horizontal line at 0, so again it cuts through there. And if I say at minus 2, which is there, oh, I've not quite gone far enough, I want to move on now, but really, you see it'll cut through there at about 0.31 or something like that. So now, if I say I've got 2 units of support to play with, I'm down to about 0.15 and up to about 0.32, 33, something like that. A lot narrower than it was with a smaller data case. All that's changed is the amount of data. Log likelihood. Right, I'm going to take a break for 5 minutes, and I'll be back up at 10:05. Just stop for a little while.